Hi everyone, Twin Beard here in the Sleep Pirate Broadcast Laboratories. I've been fooling with quite a few things, so we're gonna go over those today. First, I want to introduce you to the light bar you see on the right of the video here. That's a little joule thief, and I've set a 10mm LED into an acrylic bar. Which gives off a pretty interesting little glow, to tell you the truth. On the left, you're going to see the scope trace of what's going on there. Now, I'm just testing out, really, with this circuit. Just seeing how long I can make this last. So, you can see the joule thief here in front of us. The toroid's kind of hanging out there, the transistor's behind it. That D battery started out at 1.387 volts, 4:41 p.m. On the 14th of this month. With today being the 27th. So the only thing I've really done with this, I've just kind of let it run, and I've kept it around 22 kilohertz. Which seems to be the brightest output for the most part out of this circuit. So I've kept it right around there, and it's about 2 weeks now that it's been running off this D cell, and we'll see how that goes. I'll kick the light back off here, and then I'll sweep some of the frequencies, and hopefully you can see both the scope trace and the illumination change. Alright, now that's all the way down, and that's sitting at about 15 kilohertz and climbing quickly because it's drawing a lot of current out of that battery. This is cranking up. That's 25 kilohertz now. This battery was fresh. It would not trigger with zero base resistance. It needed some resistance to be able to trigger properly. Now we're up around 35 kilohertz. I'm going to go to my coarse tuning knob here. That pushes up to about 53. You can see barely any glow there. Barely any illumination at all now. You can't see it on camera, but I can see it with my eye at 68,000 hertz. I'm going to back this back down. That's 33 kilohertz there. And I'm going to slide it back down to normal operating range. Or where I've set for this test in any case. Not sure if any of that's clear, but that's the waveform. Delta V, delta voltage is 2.67 or 76 volts rather, peak to peak. We're at 20 microseconds per division here, and 0.5 volts per division. As you can see, here's the fine tuning knob, which is a 50 ohm variable resistor, and a 500 ohm variable resistor. Actually, that's probably a 1K in there, to tell you the truth. Little toroid, you can see we've got about 15 or 20 wraps there, bifilar. Different wire gauge. We got a 26 in there for the trigger lead, and a 22 for the power lead. Here's another one of our joule thief circuits. You can see here, this is here's our transistor, our diode. Our diode is just flashing. And we got a capacitor here in parallel. Large secondary here. Going out to another diode. And if we didn't have the main diode on here, we would be seeing a much brighter flash off the secondary. But this loop traces up out here and outside the window there. And what it's running on is what my wife likes to call this pair of magic wands. It's a wooden dowel rod with magnesium wrapped around it and a big chunk of copper. Both with leads pretty well secured onto them. So the current that this makes collects into that little capacitor, and when it reaches high enough voltage to trip the transistor, it trips the transistor and we get a little flash of light out of our joule thief. The ground moisture affects this, although I haven't seen degradation of the magnesium significantly. But the ground moisture does affect the frequency of flashing. So I kind of use that to determine what the state of the soil is. Only a couple of times has it gotten dry enough to go out. This is the FlowerPower version 2. I've got a slightly larger rotor going in there now. And then we have 2.5K here, 500, 50, and 15 ohms variable resistors. This switch will take the coil that's, there's another coil inside this case that's identical to this coil here on the FlowerPower. Two leads come out to these two terminals here. The switch will put it into a dead short condition. So it's that way now. I'm going to take it off and I want you to hear the audible difference. And this is showing Thane-Heinz regenerative acceleration effect. I always stumble over that word. I'm not sure why. Regenerative. Okay, so this is just a Bedini motor running this now, the pulse circuit, through the Starship coil, the bifilar Starship coil, 22 number 26 wire. And that's about 10 turns all the way around. So I'm going to kick this on. And immediately what I notice is the voltage on my output to my charging battery goes up. And the coil begins to kind of levitate there a little bit. So there's a push coming off of the coil below it instead of a pull. Now the rotor will accelerate like a madman, and once it exceeds the frequency that the band of this coil allows us to accelerate in, then it'll slow back down again. And so it'll wobble back and forth this way through an acceleration and a deceleration as it reacts differently with the phasing of the capacitive effect of the acceleration coil. Now, as you can see, I've been running the FlowerPower vertically here, and I designed this one to run vertically as well, and with smaller rotors too. But what I've noticed is that we lose quite a bit of friction due to the repelling action of the acceleration coil. Not only are we getting a little speed boost, but it's actually giving us a little shove vertically off of the piece of plexiglass that's underneath here is the seat. So we reduce friction quite a bit that way, and in several instances I've seen the magnet just kind of sit there and float and rotate for a while and bounce around the periphery. It does tend to take a regular pattern around this way, as though it's stuck in the torsional field that I'm pretty sure is being produced by this coil. I've seen this phenomenon before with these types of devices. with the free moving rotor of this fashion with 3 different axes of rotational freedom. What the rotor will do is it will precess around the central point, around the rim of the coil. And what I think is happening there is we have a torsional field coming up here in the air, and likewise down below, where the majority of it is being harnessed by that collection coil. And as the rotor rotates, it precesses in alignment with the torsional field, and it just kind of orbits there inside the middle of the rotor area. So I found that to be pretty interesting. I haven't really done a whole lot of testing and experimenting with this device yet. I haven't even put the power switch in yet. I just kind of got it together and started working on it. Later on I'll have a more in-depth exploration of this device. It's really easy to pop apart, so you can see all the guts and the workings. It's a little different circuit design here, and I'm going to be probably modulating that, you know, trying some different transistors and things and different diodes, particularly as time passes. So this is just a little sneak preview of FlowerPower version 2.0. I have measured when this pickup coil is not shorted, well over 2,000 volts of potential coming off of it, so things do look pretty good for this device. It doesn't operate at quite the frequency as the original FlowerPower, but that in this case is because we're using a much larger rotor which has more mass to drive, and thus more of the energy that we're shaking loose out of the subquantum C there is being forced into driving the rotor as opposed to being collected into a load. Plain and simple, the smaller the rotor, the faster you can make it go, if your rotor has a strong enough field to be able to trigger your tranny. In this case, I'm using a MOSFET with no gate driver, and with the slightly larger turns here, it's kind of odd. I'm having problems getting the small rotor, which is one of these little fellows, to trigger properly. This 1/4-inch rotor, that's the 1/8 inch rotor there, by the way, that doesn't want to do a whole lot for me. The 1/4-inch rotor, on the other hand, goes like a madman. So I'll be doing some experimentation and a little more work with that in the next video, which is going to focus just on the FlowerPower version 2.0. Thanks, guys. Have a good day. And a few more things to talk about here. Just got a friend of mine sent me these DVDs from Peter Lindemann, Electric Motor Secrets Part 1 and Electric Motor Secrets Part 2, Understanding the Lockridge Device. These were both excellent. I would recommend them to anybody out there. But just a little further talk here on some magnetic materials. This is a mu metal right here, okay, and that's a hard drive shield is what it is. There's 2 magnets that come inside the hard drive right here and here. opposite of polarity. So there's a north out here and a south out here. And what this shield does is it collects any stray flux in the area and focuses the fields in to where the head is sweeping back and forth, the head coil is sweeping back and forth here. So the thing with this is this stuff sucks down the flux, and thereby it's got a pretty steep BH curve, and it makes a very good magnetic material, and I think it'd make a very good core material. Now, what's in this stuff? Well, here's another example of it. This is in a sheet form with an adhesive on the back, and this is used to, for the most part, to shield any kind of devices from impulses. So as you can see, it'll really absorb and channel your flux really well. But this has some nickel in it, some copper like this, molybdenum, and that's molybdenum powder right there. I'm not going to open it up because it's messy. And it's got a little bit of iron in it. Iron filing. So that's what's in our mu metal. Now, I find that to be a pretty good material for cores and other uses. In fact, in this motor over here, this is a 6-magnet schoolgirl type of arrangement. These are 1-inch diameter by 1/8 inch thick magnets that are fiberglass onto the edge of this hard drive rotor, and it's being driven by this coil. But this coil has a mu metal core, and it seems to do pretty darn well in this instance. Here we have our Imitet fan. That's charging this little guy right here. It's a neat little device. It moves a lot of air too on a very small amount of current, and quite significant recovery. So yeah, mu metal is a pretty interesting material there as far as a magnetic material for core or other flux related applications goes. This is a magnetite sand that I've refined a little bit, and there's an old hard drive magnet inside here that's creating a field for you to see. But this is a very interesting material as well. It'll lose its magnetism almost immediately when you remove it from a field. Which is excellent for a fast switching transformer core, which is kind of the goal of what we're going to do in making this little bit. Here's just a chunk I cast in a cardboard box, and then I ripped the box away. So now I'm going to take a Dremel tool or something else and cut this to shape so that I can get the cores that I want to test made out of this material. And how I cast that was I poured some fiberglass resin in. Fiberglass resin in a small container, or in the cardboard box there, mixed it up with a catalyst, and then I added in and mixed in the magnetite sand. Allowed it to dry, and then we have a pretty solid workable material to work with. So this is just the straight magnetite here in a field, and its cousin over here is ferrofluid. Now, what's the difference? Well, this is mainly magnetite that's been ground to a nanoscale, okay? Tiny, tiny, tiny particles. And then been made into an emulsion with an oil. I'm not sure what kind of oil it is, but it's some kind of an oil. In any case, here's the bottle that it comes in. And this is a magnet that has a bunch of ferrofluid on it. And it's darn near frictionless in there. I mean, it's just beautiful. It's a wonderful lubricant for any kind of magnetic application. But I think it could be interesting if we were to take and put it in, say, a tube of this nature. You know, this is an acrylic tube here, and make a core out of that and see how that comes out. I don't know. It's just what I think could be a rather interesting experiment. Okay, guys. Cheers. Hi, everyone. Twinbeard here in the Sleep Creek Pirate Broadcast Labs. Just wanted to show you the latest
iteration of FlowerPower device, still running. Got a little different rotor housing going there, and we got it set up so the magnet is spinning around the Z-axis, and we're showing about 1600 volts here. That's 500 volts per division on the top, and somewhere close to 15 milliamps it looks like we're getting out of that. That's 5 milliamps per division there on the bottom. Not sure if this camera is as good as the other. We'll see though. Burr, 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 burr. And then we just got one pickup coil going on the outside there. That one is just kind of sitting on it. It's not really doing much. Cheers, everybody.
Well, I unfortunately wasted some ferrofluid here and got it on this magnet. I could wipe it off with a rag, but I might as well get some fun out of it. So I took my can of compressed air here, the kind that you'd use to clean your computer heatsink or that type of thing, and we can just kind of make it spin, which I thought was fun. So it's going pretty good there, as you can see. Just to show you a little bit about what ferrofluid can do. As you can see, I sprayed it all over my table there too. There's a metal segment underneath the table there. Let's see if I can get it clear of any ferrous materials, and we can play with this a little bit. This is a 1-inch tube magnet. It's like a donut but taller, 1-inch diameter and 1-inch tall. So it's got a pretty strong field on it. Let's see if I can get this spinning now. Ooh! Hee hee hee! I lost my straw. I might not be able to get it to spin very well. I don't know. Let's see what we got here. It goes pretty good there without any ferrous metal underneath it to drag it to a stop. I'm just having too much fun here. This moves around so smoothly here. So if you get any ideas, you can thank me later.